I'm Nathan Faulkner. I'm here with Mark, not Priya. That's not Priya. That's Mark Shaw, to talk about DC-SCM 1.0 update. Who here who knows what DC-SCM is? If you were here for the last talk, you should raise your hand. Good. Okay, almost everybody. Who uses it? If you're at Google or Microsoft, your hand should be up. Yep, good. All right. So the first few slides are just a quick recap. The previous presentation kind of covered a lot of this, but I'll go ahead and draw circles for you. So DC-SCM over here on the left side, this is where we've decoupled the security and control of server design from the compute. So essentially this means the BMC, the root of trust, they're on their own module. Part of the SCM spec also includes this DC-SCI connector. This defines all the hardware interfaces between the compute and the SCM module. And quickly revisiting motivation for why we do this. By taking things off of the compute board, you hopefully make the time to market faster for that motherboard. It should make everything simpler. It should decouple as CMOC said, we're kind of saying the same things, decoupling the cadence of your BMC and root of trust development cycle from your compute development cycle, and that can be a huge advantage. Within data center, obviously there's a ton of, a huge cross matrix of numbers of sockets, types of compute, and so you saw that this problem was just getting worse and worse. And so by trying to use a common solution across all those different platforms, it can make time to market faster for everybody. So as CMOC said, win-win. And so then just a quick recap of what DC-SCM 1.0 is. And I think this top-level block diagram directly from the spec kind of shows the major interfaces. So it's kind of the things you would expect to see. At the heart of it all, you kind of see the BMC. So most things are connected directly between your compute board, your HPM, and the BMC. And also at the heart of SCM 1.0 is the whole idea of using serialized GPIO to aggregate all the hundreds of GPIOs that are needed for different architectures. And as you can see, it's CPU BMC agnostic, number of socket, type of compute agnostic. It's agnostic. So the connector interface is defined as a DC-SCI as mentioned, and it also goes as far as to standardize on vertical and horizontal form factors. Future-proof. Attempt has been made to include a superset of anything you could need from any architecture. So what's new since last year? I think last year version 0.7 of the SCM spec was released, and as of this year now 1.0 is now released. Feedback was received from the community and implemented, and kind of the major changes Priya had pointed out were like 2 additional I2C buses and then this PCIe Gen 5x4 connection. I think the example used in the spec is an SSD, for example, is maybe what might be what you use it for. And so now we have the implementations, as CMOC mentioned. Yeah, we're making these at scale. On the left is Google's solution, on the right is Microsoft's. So I'll just go over the vertical and then I'll hand it over to Mark. So the vertical form factor you can see here, it's hard to see actually, but the motherboard doesn't have to extend all the way to the front panel there. So you don't have to use that high cost, higher layer count stack up all the way to the front panel to get front panel access. And you're able to use the lower layer count, cheaper dielectric on the SCM module there. Mark, do you want to talk about the Microsoft? Yeah.
So, to a certain extent, I look at this a little bit as defeat. Man, we have 2 form factors. But then when I start looking at all of the ecosystem, when I start looking at all the different use cases that we studied across the number of companies.
Is your mic on?
I'm like, "Who's on?" Try it again. Still nothing? I'm going to talk loud then. All right. Thanks. You know, I look at it as pretty thrilling that we got it down to 2, right? On the left side, right, 3 U boxes with heavy front I/O where you can't put, where you have to take up as little horizontal space as possible. On the right is a Microsoft version targeted at high-density compute platforms, 1 U boxes in which you need to take up as little Z-axis, Y-axis as possible, right? So there's 2 different kind of geometries that this addresses, and addresses, I think, very effectively for us. So what's worked well, right? So velocity of development is working well, right? We've developed management. I have not had to go in and prescriptively design in our management and our security across 12 building blocks at 4, 5, 6 different vendors, right? We've been able to hand them one design, meet this interface, hand them Verilog for that interface, and that's, you can imagine that saves months in validation, velocity of design, time to market. So that's been very effective for us. It's also led to some cost, some cost reductions, right? Anytime you talk modularity, right, you start saying, well, what am I going to pay for modularity? Well, in this particular case, right, it's enabled us to take what is low-speed, inexpensive things that don't need high-speed material and get them off of that high-speed material and make that high-speed material space smaller. That high-speed material in PCBs is expensive. It's growing more expensive by the generation, right? That is meeting 32 gigabit transfer per second today. It's going to double in the future. That material gets expensive. The more of the low-speed things we get off of that and optimize those PCB materials, that's significant savings for us that more than pays for the modularity that we've introduced. It's enabled us to decouple the BMC and the root of trust implementations from the servers, right? Now it's Microsoft's. We've put on that board, you can consume a board that gets you into Microsoft's data centers and meets our requirements, gets you into Google's data centers and meets requirements. I can substitute companies C, D, E, and F, right, for that, right? Because there is no single set of requirements for getting into everybody's data centers. Everybody has their own unique differentiation. And by the way, it's kind of, I'm going off script, right, but it's given us a line of sight on having common management subsystems. That's important to us, right? When things go into data centers and you have self-servers, people who are working with those data centers, having the ability to have the same firmware update, the same architecture, so that that firmware update is dealing with all your servers and you don't have 58 different firmware updates, because firmware update, I'll say it out loud, can be a virus, right? Lots of things happen. So you want one hardened firmware update that you support. And then by having a common management subsystem and having that common telemetry, right? When something does go wrong, we have common telemetry across it. We get things back into production faster, right? When we don't have unicorns in the data center and we have more homogeneity. So some of the challenges, right? Some of the challenges, DCM 1.0, anytime you put connectors, anytime you say, I'm going to put a connector, I'm going to put signals across it, how do you protect that from, how do you protect that from future possibilities, right? Because, one thing is people innovate, right? People innovate really fast. So DC-SCM 1.0 is completed. It's being very successful. We've got a lot of interest in it, but we're already looking at DC-SCM 2.0, in which we say, okay, in the future, right, we need greater virtualization because people are going to increase the number of UARTs. They're going to increase the number of, still want JTAG buses. All these buses take up lots of pins. So we're adding high-speed interfaces so that we can virtualize those and make ourselves even more future-proof for future things. Also on the horizon, right, is the prospect of multi-partition, right? As the number of cores and CPUs grows, the greater interest in protecting and dividing customers on platforms is growing. That multi-partition is also something that DC-SCM 2.0 starts to address. Now, how far are we with plug and program, right? If we have vendor A, B, and C's processors, how effective are we at taking a DC-SCM and plugging it into A, plugging it into B, plugging it into C, and guarantee that works? We've gone at least across 2/3 of our vendor spectrum, and quite successfully, right? The difference in processors isn't that big of a deal, right? the telemetry is largely 90% the same. So when we plug this into one system and we have a baseline set of firmware, we're actually very successful in getting the second one to boot, and leveraging. I'm going to make up a number here a little bit, but possibly like 90% of our firmware. 3 minutes. All right. Thank you. So we'll keep going. This has required a little bit of upfront CPLD work, right? CPLD and the Verilog between the HPM and the DC-SCM that contains the serial GPIO stream is kind of the backbone of making it work. And so getting that hardened, getting that across multiple vendors has been one of our challenges. Looking ahead, we mentioned DCM 2.0 is in work with the company, or with the OCP community. We hope that spurs even larger adoption in a couple generations from now. DC-SCM 1.0 is going. Microsoft's going to make good use out of that for up to 3 to 4 generations of our servers. That's being built into upwards of 12 plus building blocks today. Call to action. We invite you, if you are interested and want to participate in 2.0, please reach out. We want to get as much feedback as possible, because the more feedback we get, the better it is, the more successful it is. All right. Thank you.